Assalamu alaikum students. Article for today is basically an application of Ampere's law, in which we are going to discuss that if I want to determine the magnetic field due to a straight current carrying wire. Okay. Now consider that if you have a wire and definitely a straight current carrying wire, and this current carrying wire is the current flowing through that wire is in the upward direction, I is in the upward direction, then definitely there would be a magnetic field, and this magnetic field would definitely be in the circular path, definitely in the anti-clockwise direction. I've already discussed that. To determine the magnetic field for this particular case, if I want to determine the magnetic field at this particular point P, I want to determine the magnetic field at this particular point, and I know the radius is r at this particular point. Definitely the length element. I have discussed in the previous lectures all these things, that length element would be like this, and direction would be in this case is like this. And if I want to draw the direction of magnetic field, I will draw the tangent. This is the direction of B, so B and DL both are perpendicular to each other. If now in this case I want to write the if I want to write the product between B and DL, so it would become B dot DL, and definitely B is constant. So if B is constant, then taking the integral of DL, I can simply write BL, right? How can I write DL as L? Since DL is the one current element, I'm not going to discuss the integration method. I'm going to discuss it with the general formula. DL is basically the smallest length element, or the unit length element. If I add all those length elements, and if I want to take summation of that, so B is constant, B would definitely be come out, and all of the DL like DL1, DL2, DL3, DL4, DL5, DL6 up to DLN, if I sum all of those DLs, what I get? The total length, which is equal to L, right? So that's how BL arise. Now this BL is basically B would remain the same, and this L is basically equal to the circumference of the circle, right? And the circumference of circle is equal to 2 pi r, right? So the product between B dot del L, it is equal to 2 pi r into B, right? Now the other factor, mu naught is definitely a constant for a particular medium. So the last thing which is left is now the current. The current which we are going to put in the final equation, it is basically the net current. Do remember this factor, that the current which we are going to put is definitely the net current. Now understand what is basically the net current, what is meant by the net current. Consider there is a loop like this, and there are three wires passing through this particular loop, right? And fourth one outside. Two of them are having direction upward and one is having direction downward, and this one is also having direction in the downward direction. So these are the three wires which are passing through the Amperian loop, and one is outside the Amperian loop. Now how can you calculate the net current? Net current can be calculated by definitely if I say that it is having the value of current I, which is flowing through it, I, and from this particular wire I amount of current is going to pass, right? And if I say from this particular wire, third one, obviously minus I would flow, right? Why? Because the direction is completely opposite to the other. And this outer one, obviously, it is also having a current of minus I. Now, if I want to determine the net current, that is I net, this is equal to I plus I for the second wire, it would be equal to plus I, and for the third one, it is equal to minus I. I and I would be definitely cancelled out, and I net would be equal to I. Now you must be wondering that what about this wire which is outside the Amperian loop, which I have drawn in the outside the Amperian loop condition, this wire I'm talking about. Net current involves only those wires or those conductors which are lying inside the loop, inside the Amperian loop. This fourth wire, this fourth wire is basically drawn outside the Amperian loop, so it will not be considered, right? uh, all the length, if I draw another wire, there is another wire having current I, but I cannot add this wire. Why? Because this is not lying inside the Amperian loop. Net current arises or comprises of the wires or the conductors which are lying inside the Amperian loop. So overall, these three wires are going to make the net current effect, and two of them are in the same direction, one is in the opposite direction. So ultimately, the I net would be equal to I. This I is the net current which we are going to put in the Amperian's loop formula. I hope you all have understood this particular phenomena. Okay. Now, if I am going to put this value of I net into the equation, I can write B into 2 pi r equals to mu naught I, right? And if I want to determine B, then that value would be mu naught I divided by 2 pi r, right? So this is the value of magnetic field at point P, right? This is the value of magnetic field at point P. Now, there's another thing which is not definitely in your course, but I would like to share. Okay, so I have drawn the central axis, and we have also chosen three different points. One is outside, that is P, one on the surface, that is Q, and one is inside the conductor, which is S. Now I will definitely determine the values of B on all these points. What would happen? If I want to determine B, the value of B at point P, the distance from the central axis would definitely be equal to r. That means for this particular point P, B would be definitely constant, and you will draw again the Amperian loop, and by doing the same stuff which we have done in the previous article, the same stuff would happen, and ultimately what you get, B at point P, this would be equal to mu naught I over 2 pi r, right? Now, coming towards the fact that if I really want to determine B at particular point Q, and Q is the point which is lying on the surface. So for this particular case, suppose I choose that the value of R is equal to, the value over here is equal to R. So for this particular case, what will I draw? Again, I will draw the Amperian loop like in this condition, and then again the same thing will happen, and the final result would be equal to mu naught I over 2 pi r. Obviously, we are not choosing r this time, we are choosing it as to be small capital R, so the value would be replaced. what happened inside the wire or the conductor. This is the main thing which you should know. For the third case, what would happen that um, okay, for the third case, which is at point S, if I want to determine B at S, how can I would definitely determine that vector? I would definitely need to draw the Ampere'S loop. Suppose if this loop is like this, and for this configuration, what we are going to do, that we will see that how much current is going to pass through this particular Ampere'S loop. And we see that for this particular case, uh, I, which is flowing through this particular Ampere'S loop, is divided by the surface area of that wire, which is definitely a circular one. So through the whole surface area of this particular wire, current is flowing. So for this particular case, what we are going to do, we will put the value of I to be I over pi r square into pi r square. So ultimately what result, the final result which we will get through this particular case, it would be mu naught I r divided by 2 pi r, right? You don't need to go into the detail, just remember that what would happen if the conductor, if we are choosing a point inside the conductor, B would definitely be changed in this particular case. And the last point says, if suppose there's a point which we are going to choose is lying on the axis, like for this particular point, suppose this is a T point, and if I want to determine B at T, what would happen at point T? R equals to 0, and if R equals to 0, B is also equal to 0. Why? Because if you put the value of R in any of the situation, if R is equal to 0, that is lying on the axis, and what your value you are going to put for R? Definitely 0. Then the value for B would be equal to 0. So these were the four cases which we have discussed, and there's the last, the very important thing which you should know is going to be, there's going to be would definitely be that you should know that for the outside condition, like if I say that if you want to determine B in the outside situation, then there is a situation for B and R would be inverse, right? But if there is a case of inside the conductor, B is directly proportional to R. Like if R is increasing, B is also increasing until and unless we reach at the surface, right? So at the surface, what would happen? At surface, B is maximum. B is maximum at the surface. Now, how I am saying this thing, I can draw. I would say, like if I want to draw that thing with the same figure, this condition, um, for point P, this is the central axis, and if I want to draw, this is this distance, if you remember, for point P, this distance was basically we were having R greater than R, and for point Q, what we have chosen for this particular point Q, this was equal to R. So for this case, we are going to put in the equation R equals to R. And for the case which we started earlier, that is inside the conductor, this was the case for point SIS, if I'm not wrong. So for this particular case, we are having R prime smaller than R, right? This distance is taken as R prime. So this was the case which we discussed, and how can I show this through a graph? If I want to draw a graph between B and R, that is the distance, right? So what we are going to do, this is the graph between B and R. This is the origin. Consider that this point R is basically outside the conductor. There is definitely a point which is lying on the surface. This point is known as R, and 0, that is the axis. If you remember the whole figure which we have discussed earlier, this is the 0 point, axis 0 point, surface capital R, and this external point is known as small r. So this condition I have drawn in this case, and I have mentioned that initially inside the conductor what is going to happen, that if you're increasing the distance r, b is increasing. So I can draw a linear graph for this particular case. Okay, now for this case, this is the case inside the conductor. Up till that point, this is 0 point origin, this is the r point, and this is the point which we are naming as small r. So for this particular case, what we are going to happen, what is we observe that inside the conductor, what is going to happen, that b is directly proportional to r, uh, reaching at the surface point. Now at the surface point, said that b would be maximum, so b is maximum at this point. And when we get out of that particular conductor, what is going to happen, b definitely starts decreasing. By increasing r, b is going to decrease, so I will draw that like this. So ultimately what we observe, we have observed that at this point b is going to be maximum, like b, the value of b is going to be maximum at this particular point. And at this point, which is basically outside, this is basically the point which is lying outside, and the outside point can, this b point which is lying outside, right? And this point is lying on the surface, and at the surface the value of b is going to be maximum, right? So at this point b is inversely proportional to r. So that's how we can show that at various points we can determine the value of b in this particular stuff. Thank you so much for today's article. We will see you in the next application, which will be definitely a magnetic field due to current carrying solenoid. Thank you so much.